Hello everyone. In this lecture I'll be talking about more definitions of the group theory. So we continue on the lecture from the last time. Uh, I would like to say here that this example wasn't probably right because I think we like the subgroups should have so the same operator. It wouldn't be true here when we have say push 2 multiplication 9. 2 is equal to 4, which is actually not in this group. So basically, this wasn't a good example. We can try a better example. So as we said, so the multiplicative group, the 15. So here we have this. So here we have the elements 1, 2, 4, not 5, not 6, so 7, 8, not 9, 10, 11, 13, 14. So it consists of 8 elements. So here we can have a subgroup of this would be this set, we call it S. They have the operator which takes a remainder 15, like makes a multiplication, then takes the remainder 15. So we can have the set R, who's these elements. So this set, like, so if we have a group H, R, and we have the multiplication of 15, and the original group that we had is this. So here the H is a subgroup of G. And so because here we can see that we still have the identity element, so it has the identity, it has the operator, which is associative because it's already in G. And also in our case, it's also commutative, so this is even an abelian group. And here we have an inverse, so the inverse of the 8 is 2, and the inverse of 4 is 4. 8 and the 8 inverse is so the 1 inverse is 1. Yeah, that's it. So this was one of the examples that we have, and we always find if we multiply any two numbers from here, it will always be in this same set. So if you multiply 1 by any of the numbers, it remains as it is. So if we multiply 2 and 4, it's 8, and 2 and 8, it's 16, mod 15, so it's 1. And then 4 times 8 is 32, which is 2 mod 15, which is 8. So, like, we can see that every pair is also included. And also, like, 8 times itself is 64, which is 4 mod 15. 4 square is 16, which is 1 mod 15. The 2 squared is the 4. Here we can, so here we're sure that this is a subgroup. So we go, then next definition. So just a quick review of this. So we say the multiplicative group here is we put some number here, n. It means that we take all the numbers that are co-prime with this n. So here, any of this number have a GCD with 15. This GCD is equal to 1. One of the properties of the inverse is that can have we want to have a operator B inverse. This is equal to the inverse and notice here I'm reversing the order because if the operator is not commutative, then this is the right order we have to do. So the reason with this is that we multiply this. So by definition, this should be equal to the identity. So it is indeed the case if we make this substitution. So here we want to prove that this, like if we make a multiplication using this part here, it will be the identity. So then we prove that this is the same as this. That's a bit wrong how starting. So I shouldn't start by assuming that they're equal. So here I will start by making the multiplication of this value. So if it's the identity, it means that this part here is the inverse of this part here, this guy here. So here we have, because the operators are associative, we can do it and change the order of how we perform the operations. So it's B, operation, inverse, operation, inverse, which is A, operation, E. So as we see here, this part is coming from the definition of the inverse, and this is from the definition of the bracket. And this part's from the definition of the identity, and then again from the definition of the inverse. So we have this. And also the same will go if we apply it from the other side. So here we have this as the inverse. So the inverse of this part here is equal to this part. So from here, I can prove even something further. We can say that the inverse of some element A, when we apply on it the operator n times, we can think of it as a multiplication, like a power. So this is the same as this guy here. So we can prove this using mathematical induction. So for n equal 0, so this part here is the inverse for 0, which is basically the identity element, because any number or any element to the power of 0, it means we have an empty product of operations, which is the identity. Here, it's also equal to this value. So this part here is the identity, and the inverse because we have. As we can see, like E times E is equal to E, so it means that the inverse of E is also E, so that's why we get this part here. And for n equal 1, we can just use one of them as base case. It doesn't have to be both, but we can just do both. This number to the power of 1 is equal to this value, and this part to the power, so this is A, and we want the inverse of A. So it's indeed true, because both sides are exactly the same thing. So then we go with we'll assume that this part here is true for n, and we try to prove so this is our induction hypothesis, and we try to prove this statement for n plus 1. We have A inverse to the power n plus 1. So this is A inverse for n, operator A inverse. And from this definition here, we can use this part from the induction hypothesis. So this is An inverse. Then from here and from the inverse property we said in the last slide, we actually have this is equal to An whole inverse. So this is equal to An plus 1 whole inverse. So we prove this property for the n plus 1. So basically we have this satisfied, so we usually name it as A to the power minus n. So it doesn't also matter when we make the inverse operation. So the association, like we have the operators associative, we can just group the products whenever however we want them, and the inverse also like we can apply it whenever we want. But it's only when it's in the power operation. So yeah, and then we come to a new definition. So we say like the generator, if we have some group G, so and A belongs to the set F, so we make this notation here. So this is the group generated by A, which is defined as so all the powers of A basically. So this is the definition, and we have this notation as the number of elements of this set in Fortran. So in some groups, this generator could be infinite. And so this generated group can be of infinite size, or so in this case, this is if the size is finite. So one of the cases where it can be infinite, if S basically is the set of even numbers. I can just say that here. And the operator is the normal class. So here all the elements that are generated by 4 are basically the multiples of 4, and so on, which also has an infinite size. So, but in other cases, this size can be infinite. It can be finite, and we will see how it can happen. So the cases where this can happen is when we have the multiplicative group modulo some number. So it's the group we defined at the beginning of the lecture. Okay, so we remember here the elements that we have. So it's these elements from 1, 2, 4, 7, 8, 11, 13, 14. So I'll not write it again. So we can have the group, for example, generated by the 2. So this starts with the 2 to the power of 0, which is the identity element. Then we keep multiplying times 2. After here, so the 8 times 2 is 16, but we take a remainder 15, so we're back to 1. And the element is generated by 4. That's basically like that. So here, as we can see, that the group generated by some element could be of like some finite size. So it all depends on the operators and the set defined and so on. So let's say if we have a group that was generated by some element A, and we have the size of it, or we say the order of this generator is equal to m. Then we have for sure that A or m is equal to the identity element. So this will be the first repetition. So as we can see, this power sequence is infinite in size. E1, E2, and so on. So this can only be finite, like so this set can be finite if the elements are repeated. So if we pick like the first repeated element, for example, AI. So this AI, or in our case, so this AI has to be A0. So it has to be equal to A0. I mean. So why is this part true? So we can think that there's another repetition happen. So say okay. So basically, the first repetition has to be the identity element. Not necessarily can happen even before the m, but it has to be the identity element. So for example, if we have some k, so a to the power of k, so this is the first repeated element. So this is the larger k, so this is greater than this. Then we can also have this as an element in this same group. and this will be the identity basically, which is also another repeated element because it's a to the power 0. Uh, as we agreed, because these elements, like, they're not the same. I mean, so the k's are not the same. So here the k1 is greater than k2, and they are not equal. So here basically this is a different element, so it's not a0, but they are actually equal to each other. So it means that the first repetition has to be the identity element. So basically, yeah, so the first would be the uh, so so one repetition for sure is this a to the power m, uh, because if we have this, like, so we have the size here is equal to m. So here we have all these happened without repetition. So all of these are distinct elements, because if we had an earlier repetition, then the size of this group would be less than m. So here, because these are distinct, and this element is, like, we still have all of these. But since all of these are just a repetition of these, so it means that this one is the same. Like, this has to be the first repetition, and it has to be equal to the identity, what we just proved here. So basically, this is how you can show that the a to the power of m has to be the identity. Um, then I go to another definition. So as we specified, the multiplicative group modulo n. Like, this set has a size, like, by definition is equal to 5n, which is the Euler torsion function. We spoke about it before. So actually the definition of this function is exactly the size of this. So this is something that we have by definition. And as we said before, it's a multiplicative function. We can prove this multiplicative function part later. So it means that m and n are coprimes, where you can separate the multiplication like this. And phi to the power pe. Okay. So it's all the numbers excluding the ones that are divided by p. So basically it's this number divided by p. So those are all the numbers that are multiples of p in this range. So we just exclude them here. So as we said here, so the y p1, e1, so on, till pn. Can use this property to distribute the e1. Okay. So we distribute the phi here over each part of these. We'll multiply them together. And then each of these we calculate using this part here. So basically this is the Euler torsion function. So here, from combining the result from the last part, No, we can move to this part that I wanted later on, because it needs also another thing. So here I'll speak on the last concept here, which is what's called a coset. Here the cosets are, I will define them in just one direction. So when we multiply by the left, from the left, so I think it's called the left coset. So it's defined if we have some subgroup H that's coming from G. And we take some element from G here, let's call it A, and we multiply it times H. So this multiplication is defined as AX for all the X that belongs to H. So we take all the elements in the subgroup H and we multiply them times A. So this is basically the coset A. And we can see an example on that. So as we said, the 1, 2, 4, 8 is a subgroup of the multiplicative group of 15. So what other elements could we use? So we could multiply by 1, so we get the same. We could also multiply by 2, we get the same elements, it's reshuffled. Or we could multiply by 4, so the first one by 4. And 1, 2. It's 8, 1, 3, 4. So notice that here, this is the identity, and so the first element will tell us what did we use to multiply. This is 1H, this is 2H, 4H, 8H. And to get into more interesting cases, so we have also the let's say the 7H. We can multiply all of these times 7, 14, that's 13, then 11. This is the 7H. Then we can have the 14H, which is basically the same repeated elements. So 14, 13, 11, 7. And the last two would be the 13H. So 13, 11, and 7 and 13. And the last would be the 11H, which is 11, 7, 13, 13. So these are all the cosets after we take all the elements from G. We have all of these. We notice here an interesting pattern that a lot of them are repeated, and they also repeated the same number of times and so on. So this will be like a good observation for a theorem that I'm going to be proving later on. So that's it for now. Thanks for watching.